screen தெரியுதா சார்?
Yes, screen your name will be visible, sir.
Sir?
The screen share பண்ணல நீங்க இன்னும். Okay, intro முடிச்சிட்டு பண்ணிக்கலாம் சார். பிரபுதாஸ் நீங்க ஸ்டார்ட் பண்ணுங்க.
Okay, sir. Thank you. So, a very good morning to all the participants present here for the last day of the 60s AICTE-sponsored STTP program. So, on behalf of Department of Mechanical Engineering, Sairam Institute of Technology, we thank each and every one of you for your kind presence throughout the 6 days program, and we expect the same cooperation even today. So, for the last session as well as during the online test that is going to be conducted. Thank you, everyone. On this occasion, so we are glad to invite Dr. S. Dandapani, sir, Professor, Mechanical Department, Rajalakshmi Engineering College, for being here. Hearty welcome, sir. Thanks for accepting our invitation and being here to share your presentation, sir. To introduce the speaker, Dr. S. Dandapani, sir, is the Professor, Department of Mechanical Engineering, Rajalakshmi Engineering College. Served the teaching student community for the past around 20 years and having research experience. And he is one of the board member of the Sairam Institute of Technology, a member of Board of Studies of the Sairam Institute of Technology. He has a number of publications and contributions going on to the teaching community as well as the student community as well as the research field. So we are happy to have you, sir, and kindly take over the session, please.
Thank you, sir. Thank you. Thank you for the. Sir, am I audible now?
Yes, sir. Screen also visible, sir. Screen also
Sir?
visible. Yeah, yes, sir. You are audible. Screen also visible, sir. Screen
Okay,
is visible.
thank you. Thank you for
Microstructure evaluation of smart materials.
Yeah. Yes,
Okay,
yes.
sir. Thank you, sir.
Okay. Thank you very much for the group of Sairam College for inviting me and Department of HOD and faculties and introduction note there. Thank you and good morning to one and all presents for participants. Good morning. And here in this section we are going to see the microstructure evaluation of smart materials. So in this microstructure, the content microstructure, how the phase change, crystal and defects, and microstructure, microscope imaging and resolution, measurement of microstructure, general types of microscope by likely optical microscope, XRD, SEM, AFM, TEM analysis, and smart materials and transformation mechanism of smart materials, properties and components of smart materials, classification of smart materials, and application in real life. So these are the content we are likely to see. The basics, overall brief of this session, we are the microstructure, the basic elements. Already studied in the fundamentals in the material science and metallurgy and physics also, and just recalling the fundamentals and how the elements of parameter like crystal, lattice structure and unit cell, and these things are the basic parameter. How this combination of the grain boundary, these things will frame a microstructure, and how this formation and due to the external parameter like temperature, stress, strain, pressure, and this with this change, the microstructure of the material is going to be changing, and thereby the impact, the various mechanical properties, physical properties, and electrical properties all are changing due to the change in structure. So how these changes, the few things only we are more things are there, but we are likely basics only we are little bit we are touching, and the imaging, resolution, how the, and then measurements concepts. So we will see, and finally, and this microscope measuring instruments and examination likely we are seeing, And then apart from this, smart materials and how it is changing. A few examples we are seeing. And let us see, start microstructure. It is a very small scale structure of material defined as structure of prepared surface of material as revealed by optical microscope. See, it is a very small structure of the material and initially measured by optical microscope by the magnification around 25. And the metals like metals, polymers, ceramics, composites can strongly influence this. The examples are given, properties, physical properties, namely the strength, toughness, ductility, hardness, corrosion, resistance, high temperature behavior. And these can change depending upon the structure of the metals mentioned example. So these properties depends on the microstructure. From these slides, we can able to understand that. See, what is the evaluation? It is the simple determination of certain parameter like grain size, and the grain size can be measured by the coating thickness through porosity or pore structure of full characterization of multi-component system. It means any dimensional parameter or the physical and chemical parameter, and which is happened after the impact of various external parameter like pressure, stress, strain, and temperature, and thereby how the changing we can evaluate. That is called microstructure evaluation. And samples, one simple microscope sample diagram is shown, which is a thermal spray coating by plasma arc method. See this, the cross section and microstructure of thermal spray coating is shown. Some see that we can, after coating some porosity, metal oxide, unmelted particles are noted. So like this only microstructure will be available. So, and then various methods for measuring the microstructure analysis, SEM, EDEX, like XRD, these things you might be heard for research purpose and for project purpose. Then, and apart from this, lot of things are there that in the laboratory they have consultancy laboratories or research laboratories. They have these types of methods, that is Fourier transformation, infrared rays analysis, white light interferometry, rheology and viscosity measurement, high temperature testing, thermomechanical testing, zeta potential measurements like this in metallography, harness testing, physical testing, like these are examples for analytical techniques. But we are not going to see all, but one or two samples only we are going to see. And what are all the things are to be measured. And with using these techniques, likely we are measure the grain size measurement of the microstructure and identification of inclusion like tiny parts and like that porosity and bonding evaluation, how the strength of the bond, then refractory attack mechanisms and the heat impact, and then surface deposit and coatings, and then development of interfaces on reactions, and then unknown particles or materials identifications. So evaluation of material processings, and then performance evaluation and variability, then failure mechanisms and crack developments. And these are the examples. And what is it? Microstructural examination is generally performed using optical or scanning electron microscope to magnify the features of material under analysis. This can be measured. That is, examination can be measured and it is compared to some standard criteria wherever required. And the characterization, microstructural characterization means that is to quantify the microstructural features, both morphological material property must be characterized. That is, morphology means the structure, 2D or 3D, the imagination, and the image processing is the generally they are using after imaging that robust technique to determine the morphology parameter, likely volume fraction and morphology, void and crystal orientations can be analyzed. The examples are given. And what is microstructure? The term, the fundamental terms we already studied. Even though recalling, the crystal structure is used to describe average position of atoms within the unit cell. So that is the function of crystal structure, and it's completely specified by lattice types. And by analyzing we can able to identify through X-ray diffraction. And this is crystal structure describe appearance of material like the material of an Armstrong length scale, it is mentioned. We know the unit cell, what is unit cell, and it is there is simple lot of the crystal structures are there. The examples are shown: simple cubic, body centered, and face centered. See, the term microstructure used to describe appearance of material on the nanometer to centimeter length, the arrangement of phases and defects within the material. So main reason is the phase arrangement and defects are the reason to change of microstructure. So before that, crystallography, it is related with the microstructure. Crystallography is the study of crystals of formation of solids, that is X-ray determination, and crystal habits, that is formation of crystal, shape and defects crystal. This, if we study this, that is called crystallography. Crystallography with respect to material applied on metals, that is metallography. So all are integrated terms. That is crystalline materials, namely these atoms or molecules arranged in a regular or orderly manner in 3D pattern, we can say that is crystalline materials. If it is amorphous, that is non-crystalline. So in the crystallography, what are the terms? The crystal. What is crystal? Crystal means it's a solid whose constituents, atoms or molecules are arranged in a systematic geometric pattern is called crystal. The structure that implies arrangement and deposition of the atom within the crystals. So within the crystal, the arrangement is called structure. And the atoms arrange themselves in distinct pattern in space is called space lattice. So the atoms are arranged in some pattern, then that is space lattice. And it is related with the unit cell is the smallest group of atoms possessing a symmetry of the crystal. So number of unit cell will form structure, and the overall will be the crystals. And the layer of atoms or planes along with the atoms arranged known as atomic or crystallographic planes. These things we know. Just we are recalling. You see this diagram: crystal, structure, unit cell, space lattice, crystallographic planes. The input how the form based on one by one formation of unit cell and formation of lattice and formation of structure and finally the crystal form. And these are the fundamental and lattice parameter also the that is containing the 6 parameter that is a length x, y, z direction. Apart from that, these angles, interfacial angles between the length axis, that is explanation containing 6 parameter, that is lattice parameter. Atomic packing factor also, this ratio of the volume of atoms in the unit cell to volume of unit cell, that is the atomic packing factor. These are the basic fundamental related with the crystal and microscope, that is a microstructure. See, with this fundamental, how this microstructure is forming, changing from one to another. The external parameter, as I already told, the temperature or the stress due to the temperature change, and the stress strain will form, and that will act as a force, and that will, and we are calculating that is as energy. So here the solid when melting, that is addition of heating, that is we are adding the energy and it will become the liquid, and then liquid further adding temperature and it form gas. So after, so in the gas we are having some temperature, so we are extracting by releasing the heat and it will become liquid. So now the heat is present in the liquid, that is we can sometimes study the latent heat. So now that the heat is extracted, freezing, and again become solid. So this phase change from solid to liquid, liquid to gas. So the addition of temperature and cooling, that is liberation of temperature. We can say that is energy input and energy output. This is the mechanism of general principle for changing. Due to this change, the structure is changing, so microstructure automatically change. That is phase is taken to be any part of material with a distinct crystal structure or chemical composition. We can say that the different phases of material are separated from one another by distinct boundaries. So you will see how it is changing. The basic principle we have seen. The different crystal lattice structured metals such as iron is examples. Here some BCC, FCC, hexagonal examples how the phase is present. examples for BCC and examples for FCC, examples are given. And these defects, as already told, the defects is also one of the parameter to change of formation of a microstructure. So the defects is taken mean any disturbance to the perfect periodically of crystal structures. So when, as to explain the previous slide, the addition of heat or energy change, the phase is changing. Due to this, there is a possibility of defects, that is a zero defects. Lot of defects are there. Some of few are examples. 0 point defects, linear defects, only 2D, 3D, that is point defects. Linear defects and 2D planar, that is examples, vacancies, interstitials are point defects, and linear defects, group of irregular position, that is screw and edge locations. Planar defects, that is interfaces between homogeneous regions of the materials. So that like grain boundaries, external formation, the external surfaces, and then volume, the overall defects, and finally the crack will form. So this will form a new structure, and thereby the property will change. So some example, grain boundary, that is a low density and grain boundaries, high mobility and high diffusivity, high chemical reactivity. That is formation of boundary, the grain boundary will depends on this parameter. Some of the points defects seen in the previous slides are with a diagrammatic representation is shown. All the vacancy defects, interstitial impurities, foreign defects enter, and automatic self change in the unit cell, the crystals, and substitutions impurities and frontal defects. These are the defects. Due to these defects, the structure is changing, and thereby the properties are changing. How the microstructure. So apart from this change in the crystal, and how this changing due to addition of heat and liberation of heat, the solidification, the microstructure, these are the one among the parameter. Microstructure are almost always generated when material undergoes a phase transformation. About changing temperature and or pressure. What is solidification? Here, solidification process of transformation of substance from liquid to solid, in which crystal lattice forms and crystals appears. So formation of crystal and then volume shrinkage and volume contraction. So finally, solidification, that is pure metal or eutectic, takes place in constant temperature. So there is no below melting point, above melting point. Based on that, if your temperature is constant temperature, there is a change, then that is called pure metal. And so solid solution alloys are proceed over temperature range is also there. So, and this how it is changing is for the formation of initial stage nucleation and then grain growth like that. The nucleation, very small crystal, and then finally grow and as a crystal growth, crystallographic condition, and solidification, grain growth stops, and when it completes, solidification completes. So we can say the examples, the dendritic structure is the examples. See this left side, the melting, increasing energy, how the atoms disappear, and after decreasing energy and solidification, it is automatically reoriented. So this addition and liberation of the energy, changing the crystal points, crystal. So actual solidification. See this. This slide explains the energy changes liquid to solid during cooling. The energy of the liquid less than that of solid is above the melting point, hence the liquid is stable. See that above the melting point, the liquid is less than the solid. The energy of the liquid is less when compared to solid, so that there is no chance to change, so that in liquid stage. Similar way, below the melting point, the solid energy is less compared to liquid energy, so that the solid cannot change to liquid, so it is constant below the. So when the energy is less, it can maintaining the original for a long time same structure. When energy is addition or liberation, and there is a change is taking place. That is the explanation of this slide. And therefore, the melting point liquid gets converted into solid. So the transformation of liquid into solid depends on the metal melting point. Below the melting point is known as solidification. So change. So the examples are, so for pure metal, we are mold how the direction of growth columnar crystal, equilateral crystals are shown, and wall of the mold means in the castings unit, we already studied in the castings when pouring the boundary of the, because the boundary immediately contact with the green sand, so the heat transfer will take place immediately, and but when compared to center part of the casting will take time, it's a time dependent, and thereby the structure is changing. So also time parameter also dependent. So how this mechanism, nucleation, the solidification temperature, the atoms from the liquid such as molten metal begin to bound together to start form crystal. So do first the temperature applied, the atoms from the liquid such as molten metal begin to bond together and start to form crystal. So when the temperature liberation, there is a formation of crystals. The movement of crystal begins to additional temperature is living, and thereby all the crystals are joining and forming a small nucleus, and further development, and then it is crystal growth will form, finalizing. So the nucleation of crystal, then crystal growth, then irregular grains as crystal growth, and finally grain boundaries are seen in the. So this is the mechanism how the grain boundaries are forming by liberation of the temperature from liquid to solid. So examples of phase separation. Some this is the materials. Some examples: coiled chains. By heating, it is collapsed chains, and then further heating aggregates with a swollen shell. So one by one, it is swelling and form a unit, and finally further heating compacted aggregates. So the heat transfer is addition of heat, making all the crystal unity, and liberation in cooling and segregates. Already swollen, these aggregates are separating, and then further cooling, heat is liberated, so collapsed chains and fuse. So such a cyclic process, addition of heat and liberation of, that is, the heat is means here energy. So how the transformation of the crystals change the examples. So these are inside the structure. We have studied a lot of parameters, the phases, alpha, beta, gamma, that is ferrite, austenite, marsanite, bainite. So like that we studied in the metallurgy. There's few of examples. So, ferrite is soft and ductile, while perlite is hard and fertile. Ferrite is hard and stronger than austenite. Perlite is a microstructure which contains both ferrite and cementite. See, this martensite austenite is the main reason for the smart materials. Probably this formation changing the temper will change marsanite, changing whether marsanite to austenite, austenite to marsanite, changing will impact more in the smart materials. So originally named very hard and brittle. Martensite is very hard. Austenite is a structure which is above 720 degrees. That is austenite having FCC structure. So some of the examples we have seen, the parameter alpha, the grain size and grain shape, and ferrite, we are seeing two-phase, the single phase for mild steel, two-phase for dual phase steel, two-phase duplex steel, the multi-phase. These are the examples. More examples we studied, some recalling this purpose, and the methods to determine the X-ray diffraction. That is X-ray diffraction is the basic principle working under the Brock's law. That is the wavelength of distance separating the atoms in solid. That is namely with this X-ray diffraction method. That is we are coming for how the measuring the microstructure by grain size, orientation on crystals, and then distorted internally stressed crystals are there. That is, and then recrystallization and preferred orientation. So these are the from the X-ray diffraction method we can able to predict. And then who are all the founder? Just the knowledge. So Wilhelm Röntgen studies X-rays, that is Crookes tubes, and then Max von Laue established crystal diffraction. Then Paul Peter Engel's thesis. So these are the people who has developed X-rays and using the William Lawrence Brock he has framed the Brock's law. And Brock's law, based on the Brock's law principle, only the XRD is functioning. And then Peter Debye and Paul Secker has found this Debye sketcher camera techniques. These are the founder of this techniques, X-rays, based on the X-rays. How the diffraction works. The X-ray diffraction principle, basic principle is X-ray is supplied to the lead screen. X-ray beam is focusing, and when it's supplied through the small slot and focused on this crystal, and it is diverted photographic plate, it is diffracted. Brock's law is coming is to when it touch the crystal, and from the shape and angle we have studied the various crystal nucleation, grain growth boundaries, and based on the grain boundary, the angle will vary. Based on that, based on the shape of the boundary, the reflection will take place, and thereby we can identify the shape of the. So, example, X-ray diffraction methods. With these are the general used in investigating methods. Crystals, various solid, they are live photographic method. There is two types: transmission method, back refraction methods, and then Brock's X-ray spectrometer. That is rotating crystal method, and also powder method. There are totally 4 methods. Just they have general they are explaining. The crystal structure methods by Loy method. There is a oriented single crystal. See there is a Loy method, rotating crystal method, powder method is there. The Loy method here, X-rays are supplied from the source to the crystal, and then finally the screen is presented. So crystal, see Loy method, there is a 2 methods: transmission method and then back reflector method. So let us see the transmission method. There is a X-ray beam is coming, and there is a screen is there. After that, crystal. So in between crystal, or which we are going to measure element specimen, and the X-ray beam, there is a screen. So between screen there is a screen, but not between screen. Between X-ray and specimen there is a screen. Then that is transmission method. If it is the screen is crystal is let us the another method also compare. Back reflection method, X-ray. See the diagram. See the diagram. The X-ray and single crystal, in between there is a film. That is a back reflection method. So in the back reflection method, the film is placed between the X-ray source and the crystal. The beam which are diffracted in backward direction are recorded. So now the X-ray is going through the film. There is a slot is there, and it is impacted to the crystal, and thereby crystal forming a cone shape. That is called a Louis reflection. Is defined by the transmitted beam. The film intersects the cone. Then so the cone shape, the reflection is forming, and where the film is touching that cone, imagine, and you can see that is a hyperbola form. That is the concept of Louis method. So from this we can able to predict the crystal shape of the microstructure shape. And if you go for this method, transmission method, there is a film is produced behind the crystal and record beams, which is film is placed between the crystal and the record beams. See this, it is X-ray is coming, and immediately crystal is there, and then screen is. But in this method, there is a film is between X-ray and crystal. But here, X-ray, after that specimen, that is crystal with specimen, and then film. So in this method, the reflection is different. The cone of Louis reflection is defined by transmitted beam. The film intersects the cone with the diffraction spots, generally lying ellipse. So these are the 2 different methods. Just we are highlighting the methods, not we are discussing deeply. And what are the impact output this general output is a film image are shown. One is coarse grain, that is below 0.4, few clear points, that is B1, B2, that is diagram number. You can see this B1, B2, very small rectangular box. 5 boxes there out of first two. Box 1, box 2 is the coarse grain, and box 3, the fine grains. Box 3 is the fine grains, and box 4, that is cold, very fine grains. Box 4 is very fine grain. Box 4 and box 5 is cold work. The spots are more irregular in outline and shapes. That is box 5. And distorted crystal, and finally outer distorted. How the crystals based on the grain size, whether it is coarse grain, fine grain, very fine grain, cold worked, irregular, that is irregular pattern, distorted pattern. The examples are in the boxes. These are the Lowy methods. And then we can come for the another rotating method, that is powder method. Powder method is third one. We have seen this rotating crystal method, powder method. Lowy method, 2 types, and rotating crystal method, you'll see this. This is the powder method. This is powder method, third method. Powder diffraction is a scientific technique using X-ray, neutron or electron diffraction on powder or microcrystalline samples for structural characterization of materials. An instrument dedicated to performing such powder measurement is called powder diffractometer. When X-ray is shined on crystal, it diffracts in a pattern characteristics of the structure. In powder X-ray diffraction, the diffraction pattern is obtained from a powder of the material. So generally, X-ray will focus on the crystal, a single crystal, and diffracts. But in powder method, the powder only sample is in the powder form. So it will fall on the powder, and from there it will diffraction will takes place. So here X-ray is going, and the green color is the sample. You can see, and the cone shape, the formation is a double side, and this is a film shape is in the cylindrical shape. That is a film shape. So where the diffraction in the form of cone, and where this film is intersecting, and that place the fringes are forming. See that in the rectangular shape below the diagram, that is the front view, they are showing the fringes. That is a point is there, that is slit point, that is a X-ray entering point, black color, and the point where incident beam enter, and as concentric circles arc like fringes are forming in the film. So you are seeing the degree, that is 0 degree one side left side, and 180 degree right side. So like this we can able to, based on this rectangular shape fringes pattern, we can bring to come to conclusion that whether it is BCC or FCC, like that. We can able to see in this left side diagram, there is a incident X-ray is coming, film and specimens, a 2 theta angle, exit X-ray, and film A, left side A diagram, B diagram, and after the top view, that is the front view, after the film imagination, the fringes, how these we are in the X-ray diffraction, we are studying the theta angle. The angle is noted like this only. And with this, we can able to see the notation, see BCC, very small BCC and FCC structure. Below the rectangle, bottom rectangle is FCC, and above the rectangle is BCC. Like that, we can able to predict the structure using this method. And then another crystal type, how to calculate from this calculation, the Brock's law, from the spacing of the line on the photographic film and known dimension of the camera, the apex angle of radiation are calculated. So the photographic film, using this formula, the D is atomic plane, integer, spacing of the atom planes, wavelength. Using this formula, it satisfies this formula, and also we can able to general relationship between wavelength of X and angle of incidence spacing between the crystal layer. That is, Brock's law is implemented to predict the pattern of the film formation. This is the rotating second method, rotating line method. So we have seen Lowy method and powder method. That is 1 and 3, and this is 2. Second method, rotating crystal method. This is similar as previous only, but X-ray source and the film is there, and then finally there is also crystal inside. The reflected beam will rotation by rotation of the film, and there is a so these determine the shape and the size of the unit cell as well as arrangement of atom inside the cell. So this will get by rotation. We are throughout overall 3D structure we can able to predict, like lattice constant of the crystal, arrangement of atoms. We are not going deeply, just we are highlighting the method. And then microstructural examination is generally performed using optical scanning electron microscope to magnify features of material under analysis. That size features can be measured, quantified, general types. So I already listed some of the practically more research people are doing these methods. Diffraction, that is Brock's law, already told that based on the Brock's law, when it concept explained by Huygens principle and defined as the bending of wave around the edges of opening or obstacle. When the X-rays are impinging, that is light reflected over the slot, and it will going to be the bending of wave will form by the edges of the opening. Edges of the opening or obstacle means if any circular hole in a plate, when you are applying a light rays, when it touches this periphery or boundary edges of the hole, and it is diffracted, bending will take place. At anything experience this phenomena is a wave. Applying theory to light passing through a slit. Slit means here the hole. We can prove it is a wave. Then only we can say that is a wave. See, the light of electrons is coming, and the object diffracting, creating small dotted lines, hidden lines like that. It is the gap is slit. That is a hole. When it comes after that, it is diverting. Red color, blue color, green color, like that. Bending of waves is taking place. Some angles, theta angle plus theta minus theta angle, like that. And finally, it is electromagnetic lens of electrons. That is lens. It is falling over the lens, and then it is diffraction pattern at the focal plane. It is forming, and how much angle plus theta and minus theta, all the waves are joining at diffraction pattern. And finally, in the film magnified images, this is image we can able to predict the result. So this is the basic theory of imaging diffracted spots. That is a distance u, v, f, the distance from the object to lens to output, and the center focal. This is related with the Brock's law connecting. See that the image formed. Image formed when the equation, the 1 by u, 1 by plus 1 by v equal to 1 by f, satisfy the f is focal length. So here f is the focal length of the lens. So d theta and theta, that formula, Brock's law formula, radiation with wavelength lambda is incident of the object. Then each slit in grading scatter radiation in variety of directions. So each slit is diverting the, bending the waves. Radiation scatter in given direction is collected by lens at a distance u distance from the object. That is what we have seen, they are explained in the sentence. So finally, the condition d theta that Brock's law satisfied, the constructive interference occur at a bright diffraction spot will appear at the point. So this is the basic principle of the diffraction. So using this various diffraction, this scanning electron atomic force microscope, scanning electron microscope, and transmission electron microscopes. A lot of microscopes are developed to measure the surface 2D, 3D, and inside imagination. More parameters. The examples here, solid solution containing hematite, iron oxide, and limatite, iron, that is, which is formed olden days. It's a very long rock, that is a olden rock. Sample of mineral titanohematite, a solid solution containing hematite, iron oxide, and limited titanium ion, as this mineral cooled very slowly over a period of 1 billion years. So this mineral, 1 billion years cooling, then formation of lamellae, and that is ilmenite and hematite exolvent. This is caused by the gradual reduction in distance over which atoms can diffuse as the temperature decreases. It's a prolonged cooling, the formation of limatite and hematite, and there is a swelling of the platelets, decreases platelets formed at high temperature are thick and widely spaced, whereas those formed at a low temperature are thin. And see, there is a cooling where is the temperature is high and that area thick, and where is the temperature is less, that area is thin. Thick area widely spaced, thin area closely spaced. So this imagination, that is formation, but how the imagination techniques, the instrument is working for low magnification. Example, see, two-phase intergrowth of etched limonite hematite is this first image shows dark patches show where hematite lamellae have been preferentially dissolved out of the limatite host. That is, the major is a limatite over which hematite is dissolved, and the black color lines are showing the dissolved hematite over the limatite. And the second imagination, that is medium imagination. So this is low imagination. If you make it medium low imagination, for example, 22 magnification and 1 mm, and whereas medium 500 magnification, 10 micrometer. So the same, the black color line magnified higher. So in the black hematite also there is a, see, the dissolved hematite lamina which itself containing fewer limatite plates. So even though it is consumed, the hematite is consumed by the limatite, even though there is a little bit of limatite is present, by we can able to see by magnification size. So the same one, but the magnification will reflect this. From this we are able to understand, based on the magnification we can go for higher details. So here high magnification like 10, this is transmission electron microscope. Imagine the hematite plates in a limited host. Note that length of scale platelets decreases from left to right. See that from the TEM image we can with these sizes reaching 1 to 2 nanometer units. Hematite is 1 to 4 nanometer. So we can see the scale length. So this image we are explaining low magnification, high magnification, and then medium magnification. So with these two slides we can able to understand magnification is the important factor in the microscope. See, measurement of microscope, there is examples for depth and surface. Depth, the first group include measurement of depth. Initially the hardening thickness, surface treatment, how much depth is, gas depth examination, how much it is depth we can able to measure by depth of vaporization, depth of surface hardening or coating thickness. These measurements are made at a specific location, may be subjective to considerable variation. So using microscope we can also able to measure the depth of hardening and also surface. This is second group of measurement belong to field referred to stereology method. The surface is the body of measurement describes relationship between measurement made on two-dimensional plane of polish and three-dimensional microstructural sampled. So depth also possible, surface 2D, 3D also possible. So One example for surface stereology method. Stereology is the three-dimensional interpretation of two-dimensional. So in the 3D solid, but we are considering the 2D surface cross section of material tissues. It provides practical techniques for extracting quantitative information about 3D from measurements made on two-dimensional planar section. See how the stereology, one sample is given. See whether it is a circular. On the microscope, we will draw a circle or a rectangular. Within the rectangular, how many grains crystal are fully covering. Here, this microscope illustrates grains counting procedure for that is called a planometric method using rectangular. There is stereology method. Under this, planometric is one method. Here, this NA, that is a numerical aperture, which is the data related with the stereology standard based upon 53 grain completely inside the. So inside the rectangle there is a 53 fully covered. Remaining one half 43 in the boundary there is a half of the grains, half portion of the grains. So 43 grains like that. So intersecting the lines and one full corner grain from the contribution of the 4 grains intersecting the corner. This is a corner. Sometimes there is a, see that 3 triple point also will come. That is a two grains. This the boundary line is 2 grains. If 3 grains are coming this point, that is a triple point. So like that also there is a calculation. So here based on this 53 plus 43, 43 is counted as half. So 43 divided by 2 plus further the one full, like that they are calculating, and there is a standard table to for calculating the working distance. From the table they predict that the working distance is 5.1 for the total length of this. Based on that they will explain for this distance so much of grains, and based on that we can able to say the density or grain, the atomic factor, like that we can predict. So these are referred from this reference. And measurement, see the International Society of Stereology, there is a standard is there, and the table is listed. From this we can able to predict the notations, and there is a formulas are there. From that we can able to, using the formulas data, we can able to predict the volume and the length, dimension, 3D value, everything we can able to see. Some synthetic microstructure of uniformly shaped, identical size, spherical particles in a matrix phase. The test area is 12,100. That is horizontal, 10 horizontal, 10 vertical. Each 110 into 110. With this surface area, how much the spherical matrix are calculated. Like this, there is a one step is given in this. As already explained, the rectangular, here it is a circular. Within the circular, the example of grain size measurements by planometric method, micrograph at 100x magnification of austenite manganese steel that was solution annealed 1040 degrees Celsius. So annealing was done, and then aging process at 620 degree to decorate the grain boundaries with the fine pair line. So there is a austenite annealing and aging and formation of fine pair line, and after that they tested the circle has a diameter. This is standard size 79.8 mm. Like that they make concentric circle also. So standard size as per the seriology method for the area of 5000 mm square. A count is made to determine the number of grains completely within the circle. So in this circle 44 is fully available, and the intersecting circle is 25. It is half of the circle. And then as per this for 100 magnification, multiplier is 2. So based on the magnification there is a standard value. The number of grains per square millimeter is for unit 1 per calculating per unit into 2 into 44 plus 25 by 2. 25 by 2 means that is the half of the value, and thereby 2 is the multiplier as per the magnification size. So and then we are 113 from the table for the 113. There is a formula. One from the grain size formula 3.3 to calculating. We are rounding into grain size 3.87. Like this, there is a method to calculation, evaluation, microstructure evaluation, grain size evaluation. Generally, the equiaxed elements, planometric method is used. For non-equiaxed, intercept method. Intercept method is both are under stereology methods. Non-equal grain structure require measurements on the three principal planes: longitudinal, planar, transverse. Non-equiaxed means if you see some of the grains maybe approximately even, uniformly, or homogeneous or heterogeneous like that, I think it will be they will predict not assure but equiaxed, and we also see the dendritic growth equiaxed grain structure like that. Maybe the symmetrical shape axis of both side, the same shape of boundary will be same, then that is called equal. If it is not like that, then that is called a non-equal. The example of grain size measurement using intercept method. This is intercept method. Previous scene is planometric method. So here the three concentric circles have diameter, this standard diameter as per the seriology standards, and total line of length 500, and magnification microscope 500. Magnification is 500. Here they are using like this. For example, hence the true length is 1 mm. A count of number of grain boundary intersections. Several are not well. It's not 100% predicted, so that they are telling not well delineated by the Nittel H, a common problem in such ratings, especially if automated devices. So automated devices, we are not assurance that how many grains are covering inside for approximately 60 grain boundaries intersections. 7 triple line. Triple line means, as already told, the grain boundaries. They like this. When it is coming like this, when three grain boundary, grain 1, grain 2, grain 3, the triple line, the point is triple line. So how many lines are there? And for that, there are 7 triple line junction, and 7 into 1.5, that is called as 1.5 plus 60, and they are getting this value. So for calculation formula is there, and as per the formula PL 1 by PL like that, finally they are rounding to 8.9. So there is a method. So from these slides, serialization is one method, and there is a 2 methods, planometric and intercept method. So like this, one examples we have seen. So for optical microscope, this is the starting of the microscope initially as a light microscope, a microscope that commonly uses visible light and a system of lenses to generate magnified images of small objects. So the object is placed a stage and may be directly viewed through 1 or 2 eyepieces of the microscope. See, the principle we know, just to focus a lighting system on the object, and we will get the images on the films. See, that is the best resolution of an optical microscope is 0.2 microns. Maximum magnification is limited to 1000x because of limited resolving. So beyond 1000 magnification is not possible. So that is the drawback of this optical microscope. So then there is a how to prepare a specimen. You might be studying in the metallurgy also, just applying chemical etching agent for the cleaning purpose, then only surface will be clean. The specimen is dipped in etching agent, which is immersion method, rubbing cotton soaked in etching, and electrolytic etching. Any method you have prepared the polishing machine using polishing. The etching agent examples are given of potassium hydroxide based on the type of material. This, for example, it is shown silicon. This type of etching agents we can. Then the specimen is the object being examined. Then most specimens are mounted on the slides. Slides means specimen we cannot hold by hand, finger, so that we have to provide a supporting holder. So that holder is made by the mounting machine. The specimen and the holder will be prepared using this molding machine. So that is the purpose of molding. After this, we can take the specimen and we can use it. Then X-ray XRD. the XRD, that's the general, as already explained, this X-ray diffraction Brock's law concept. Using XRD, you might be seeing what are the, from this we can find crystalline phases and crystalline and amorphous materials and structure of crystalline material and the electron distribution, atoms throughout. Like this, lot of advantage. We can find the thickness of thin films, multi-layer, orientation, like various advantages are there. This is working under Brock's law. So these are the examples. Rikaku is a company name, and they are how to predict after this X-ray diffraction result. From this result, we can confirm our chemical element is present or not. See how there is a JCPD, Joint Committee of Powder Diffraction Standard table is there. Using that, these are the data which are related with the output of the X-ray, the graph. So, for example, it is shown. For example, boron carbide at the 34 point. This result is taken from the XRD. Now, this 34.71 is available in the. This is the JCPD standard table. If this degree is available from your output, then you are confirming the boron. If it is not available, then your material is not there, or it is not properly impacted, like that. So confirmation. So like this XRD we can read. So XRD graph, and what are the this is Miller indices. These are 11200220 are detailed crystal structure, Miller indices and things, angles. This scanning electron microscope. This we know 1000, beyond 1000 we can go for here maximum 3 lakhs magnification to provide with high quality. Sir, anything is there? Sir, audio is there? Sir? Sir? Hello? Sir? Sir, audible? Sir, Shanmugh, sir?
Hello.
Sir, audible?
Yes, sir. Audible, sir. Audible, audible. You continue, sir. Audible. Audible. Okay, okay. You continue, sir.
So, we have seen up to
Slide number 53.
Uh,
Yes, sir. 53.
This one. Yes. Scanning electron microscope. So these electrons interact with atoms in sample, producing various signals that contain information about the surface topography and composition of the samples. So this is the comparatively optical microscope it is developed, and 2D is possible. But whereas in AFM, atomic force microscope, there is a cantilever with very sharp tip, the inside mechanism. This cantilever is the inside mechanism of how to touch the surface of the boundary, grain boundary, are contacted with the cantilever, and to sharp screen tip to scan over a sample surface. As the tip approaches the surface, the close range attractive force between surface and the tip cause cantilever to deflect. So based on the deflection concept, the atomic force microscope is working. So with this atomic force, we can able to predict 3D also, 3D and 2D. But scanning electrons, 2D, atomic force, 3D also possible. Transmission electron, there is 3D also. Transmission electron is interdepth comparatively atomic force magnification, transmission electron microscope will highly focus, as already we have seen. There is three images: low magnification, medium magnification, high magnification. High magnification, we are seeing the total details, length of the hematite, limitite, like that we have seen. Similarly, if you go for TEM image, we can able to the depth, clean shape of the geometrical shape of the microscope data we can predict. So these are the electron microscope scientific instrument that use beam of highly energetic electrons to examine objects at a very fine scale. This is general advantage. The examination can yield information about topography, morphology, composition, and crystallographic information. Topography is a GPS, like GPS 3D image, and morphology, that is a surface, and the chemical composition, and inside detailed information of. So mainly there is a TEM and SEM. The TEM allows one study of the inner surfaces. SEM used to visualize the surface. So this is outer surface, this is inner structure. So SEM working, this is the electron gun, and there is an electron beam, and then first condenser lens, and then second condenser lens and deflected coil. When the electron gun consisting of cathode and anode, there is a cathode anode. Then when the electrons from the source, primary electrons, are impinging on the surface of the specimen, then there is a diffracted, based on the shape of the grain boundary or crystal structure, there is a diffracted electrons. Secondary electrons will fall, and that will focus. See the length, the electrons is focused using the object lens, and it is focused on the sample, and diffracted image will focus on the screen. That is reflection. Here the condenser lens control the amount of electrons traveling to down column, and the object lens focuses the beam, and bringing after final deflection coil helps to deflect the electron beam. So it will deflect, and SEM attracts the secondary electron. Finally, the additional sensor deflects backscattered electrons and X-rays. See, backscattered means that is the result output. That is in the screen, image screen. We can able to predict the the image of the boundary of the grain structure or crystal structure. See how to the preparation. There is a example sample coated with thin layer of conductive material. There is a material, conductive material, and there's using a device called a sputter coater. It is small chamber, that is vacuum is there, and the gold foil is placed in the instrument. Applying the using argon gas, there is a coating is made, gold coating lightly, and argon by positive, making a positive negative principle, and removing the argon ions, then become attracted to negative. So this is the principle how this coating is taking place. These are the samples are coated. So after this only the specimen is subjected to SEM. So advantage and disadvantage. So detailed 3D and topological imaging, versatile information from different detector and instruments work very fast. And modern SEM allow greater for the generation, of data in digital form. So SEM most require minimal preparation sections. Disadvantage: SEMs are expensive and large. Special training is required for this SEM. Preparation of samples can result artifacts, that is some artificial defects, and because we are dealing with the gas, argon gas, SEM are limited to solid samples, carry small risk radiation exposure associated with the electrons. So for TEM, there is a fixation, rinsing, dehydration, embodying, trimming, collection. Let us see through the diagrammatic way. That is easy. There is a plate and a grow cell. That is the fixation. We are fixing with the chemical, and then preparing dosing. That is the rinsing and straining, treated with heavy metal components. There is a procedure. Then dose cell with the LP. That is dehydration, washing and increasing ethanol, followed by final wash, another polar substance like propylene oxide, like that, and then rinsing, palette, fixing, post final specimen is embedded in resin and curing in vacuum, and finally trimming, and then thin section sample trimming, and it is ready for preparation like this. So this is the methods, and we are highlighting just overall going roughly, and then TEM working. The working principle similar, more or less similar as the SEM, but the electron source consists of cathode and anode, and the cathode tungsten filament which emits electrons when being heated. Then negative cap conforms the electrons into loosely focused beam. So this beam is then accelerated towards the specimen by positive anode. See, same concept of the negative and positive based the magnetic lens and the vacuum. Inside the vacuum, electron is tightly focused using electromagnetic lens and metal. See this electromagnetic lens. There is a object lens and projective lens, and then there is a phosphorescent lens. And with this, the TEM is working, but TEM is somehow highly magnified. 3D internal structure are possible. So vacuum concept is highly here, but whereas a small area of vacuum is placed in SEM and AFM, but here the area of the vacuum is higher because to interstructure are to be analyzed. Some of the samples, the yeast cells, how the microstructure is samples. Yeast cell different TEM image, SEM image, and TEM image, SEM images. You can see the difference, SEM image and TEM image. TEM image will give you detailed single element, rough size of SEM image. Microscope image, this is optical microscope. So the three diagram explain optical microscope, SEM image and TEM image. Like gel-like fluids generate most chemical energy needed to power the cell biochemical reactions. That is TEM image, and then TEM image of that is a biomedical name, Mitochondria. That is like this. These species known generally as a common fruit fly or vinegar fly, based on the fruit. That is the analysis where images are shown, the biomedical images, and these are the some atomic force through 2D, 3D, nanoscale, 3D topography, intermolecular forces. This is the principle inside how the tips are working. Like we have seen in the SEM, there is a cantilever movement, how it is working. The detailed picture is given. Some sample images, 2D, 3D images, and AFM image, 2D, 3D image. This is TEM image. TEM image based on the relation, the multi-wall carbon nanotube are shown at 600, 200, and 600 image. K is the that is a space resolution 200K, 600K. Smart material. Then we have seen so far based about detail regarding data of the microstructure, and we will come for the smart material. The first recorded observation of the smart material transformation was made by gold cadmium. That is, and then further it is changed brass, and that is also on further development nickel titanium. That is finally nitinol is the prolonged name of smart material in the olden days, and thereby developing the nitinol was found initially. That is first how it was smart material transformation in 1932 and 1938, and then 1962. Finally, the inside concept is the change in microstructure, marsantites to austenite to marsanite. How? By applying heating, cooling, and deformation. This will change by application of temperature. So heat recovery, cold recovery, that is cold marsanite, austenite further cooling, it will core marsanite deformation. So here the shape memory effect and super elasticity is the one of the parameter of the shape memory alloys. When only the copper based alloys came close challenging nitinol family, initially nitinol family is very close to copper based alloys. During 1980 and 1990, the number of companies began to provide nitinol, the titanium nitinol material and components, and increasing number of products, especially medical products, were Now, as per now, it is developed, and let us see the basic transformation. Arsenide, high temperature phase, a cubic crystal, and when it's low temperature, and it will be martensite. So arsenide at high temperature phase, martensite low temperature. Two different forms, martensite materials, tuned and detuned. There is a tuning and detuning. A certain temperature, small material will stay at a thermodynamically stable phase. See, certain time there is no change. Due to this transformation mechanism, small material have many special properties such as shape memory effect and supervelocity. See, by applying the temperature, it is changing the arsenic martensite to arsenide by way of tuning and detuning. There is a different phases also. The transformation mechanism of the this is the basic principle of the smart material. So tuned martensite phase undergoes external stress. So when the external stress, whether it is temperature, pressure, or anything, transformed to detuned, that is one. There is no temperature during transformation. So external stress with the based on the stress, it is a change tuned to detuning. There is no need of temperature, any stress. But when the detuned material undergoes increasing temp, so detuning undergoes by application of temperature. Detuning martensite will change it to arsenide. Then arsenide will go back to tuned martensite. So again further arsenide change to tuning. So this cycle will take place. So temperature adding, detuning change martensite to arsenide, arsenide to detuned, tuned martensite, tuned to detuning. There is no need of temperature, only external stress. Due to this temperature, there is a formation of strain stress that will impact the changing, detuning, tuning. So these are the graph for notation. Martensite finished temperature, stop temperature, arsenide stop. How the same mechanism is explained. The tuning, application of temperature, change in detune to arsenide, arsenide to tuning. Tuning to detuning, there is only the problem is because of temperature there is a stress strain. So supervelocity is another important property material, smart material. When the arsenide finish temperature relative to very low, the supervelocity material will stay as arsenide under room temperature. So this arsenide phase range, the supervelocity material can transform to detuned material. Same concept they are explaining, and the supervelocity principle is related with this detuning arsenide arsenide. In the graphical representation with the starting and ending temperature. And this is also the because of temperature there is a formation of stress strain. How will the stress strain impact in the stress strain arsenide and martensite, and the super elasticity behavior with the graphical representation. And then smart materials we come for intelligent materials. So smart material, how the parameter like simulation, what are the simulating parameter like temperature, pressure, electrical, magnetic, and light mechanics. These are the parameter to simulate the smart material from one form to another. When the temperature or pressure or electrical current or magnetic, and this will change the smart material. What is mean with smart material? Means these are the smart materials react to change their environment. Smart system are produced designed to react to change. This is the example, that is can respond heat, light, moisture, electric, magnetics. So how these are the simulating element, and what is the impact? Color change, light emitting, moving material, temperature changing, thickness changing. These are the output. Input are these are the parameter: temperature, pressure, moisture, current, strain, stress. Output is color change, light change, moving temperatures. Smart structure may have sensor, that is simulation actuator. So there is a 3 degree of smartness. So let us see
Hello.
Hello, sir. சொல்லுங்க sir. Hello. Yeah, Dandapani sir. Hello, Dandapani sir. Audible இல்ல.
Hello.
Yeah, சொல்லுங்க.
உங்களுக்கு இப்ப கேக்குதா சார்?
கேக்குது சார். இப்பதான் கேக்குது சார்.
Yes.
கண்டினியூ பண்ணவா?
Yeah, பண்ணலாம் சார். பண்ணலாம் சார். நோ இஷ்யூ சார்.
இருங்க இது கட் ஆயிடுச்சு. நீங்க
ஓகே.
ஆமா.
ஓகே.
ஷேர் ஸ்கிரீன் போட்டுருங்க. ஓகே சார். ஸ்மார்ட் மெட்டீரியல்
விசிபிள் சார்.
மேக் இட் ஃபாஸ்ட். ஃபாஸ்ட் பண்ணிடலாம் சார்.
இன்னொரு 5 மினிட்ஸ் எடுத்துங்க சார். 5 மினிட்ஸ்.
See, disadvantages smart materials, and these are the parameter: stress, strain, temperature, electric field, or the hydrostatic. These are the simulating elements, and these are the applications, and these are the disadvantages also there. See, it's relatively expensive to manufacture and machine. Most smart material have poor fatigue properties and the loading condition, but comparatively these smart materials are lagging for the, because the steel components more survey than 100 times comparatively smart material, so which is better. So small, this is some disadvantage. The properties: sensing material and activation of material, controlling devices, self activation, shock absorber, damage arrest, and these are the self corrective, these are the advantage properties of the properties: piezoelectric, electrostatic, magnetostatic, thermoelectric, shape memory alloys, photochromic, thermochromics. These are the type of smart material, and the input are the deformation, potential difference, like the simulation elements. These are the types, and these are the input is a simulating element. The output is the same deformation or potential difference. So in this slide, components of smart system, that is electronic based, their data acquisition, data transmission, command and control, like the wiring system also, the computer database wiring, or internet cables also one type of smart category, smart material category, because the aim of this component to collect the required data and the appropriate sensing and monitoring. Fiber optic sensing, example, the purpose data transmission means to forward the raw data to the local and central command control units, like this. And then a brain, it is a controlling element acting as a brain. And then this is the data instruction, motor service, action devices. So these are the function of the smart material. So let us see some images, some paper from the paper, journal papers, how the impact of the piezoelectric material shown. The image one shows without piezoelectric, image two the developed piezoelectric material, that is namely KN and KT, NTK, that is from the reference paper, explains that there is a application of the simulation of the piezoelectric concept of the smart will enhance the properties of the material. That is the concept explained in this paper. And this is also same explaining the improving piezoelectric properties by controlling phase structure. So the smart material, how it, the simulation, how it impact is explained in this paper. Same things explained. Let us see this some of the videos and examples of the smart materials, how the heating, smart heating, it will changing, and stress induced and deformation, and that is shape memory polymer, how it is changing, and then cooling under stress, stress is removed and recover upon triggering, and then next cycle. So cyclic is going on. So like this smart material polymer unit, and let us see, let us watch some videos. Yeah. Last one. Play button.
Sir, excuse me, sir. Sir, audio, கேட்கல சார். ஹலோ
ஆடியோ மட்டும் வரல. நல்லபடி சார்.
ஆடியோ வரலையா சார்?
இல்ல, ஆடியோ மட்டும் வரல. நீங்க வீடியோ தான் பண்ணிருக்கீங்க.
வாய்ஸ் கேக்குதா?
உங்க வாய்ஸ் கேக்குது சார். அவரு
ஸ்லைட்ல உள்ள வாய்ஸ் மட்டும் கேட்கல.
அப்படியே அது இப்ப ப்ராப்ளமா இருக்குன்னு நினைக்கிறேன்.
இல்ல, பரவாயில்ல, விட்டுருங்க சார்.
இதுல போட்டுருவா பேப்பர் இதுல போட்டு அடுத்தது. Let us see some examples. We will complete this.
Okay, sir.
Natural piezoelectric materials, and which are naturally available. The examples are sugar cane, topaz, and this DNA. And these examples are given some when subject to an electric charge or variation in voltage. Piezoelectric material will undergo some mechanical change, and vice versa. This is the example for the piezoelectric materials. And then the electrostatic materials, how the static force are in the examples in the bottles also. The material has some properties, piezoelectric material, but the mechanical change is proportional to the square of the electric field. See, the characteristics will always see the example when rotation, there is also a because of static force, it is contacting the surface of the wheel. It is going on in the bottle, some metal bottle, some things. There is a electric static force also there, and these are the one among the smart material data simulation. And examples are complex fluids for rheological materials. That is also one simulation, rheological. There are in liquid phase which can change the state instantly through the application of electric or magnetic charge. These fluids may find application in brakes, shock absorber, and damper, and vehicle seats. There is a fluid is there, and we are applying electric current or magnetic current, or and thereby this functioning. The concept of rheology is the science that concerns the flow of liquids and deformation of solids. So rheology means rheo means to flow, logo means science, logy means study of. So the flow of science study based on that biofluids, personal care products, electronic optical material, pharmaceuticals, everything are examples are given. This is a one simulation of the smart material. And magnetostar material, based on magnetostar subjected magnetic field, vice versa, the material will undergo induced mechanical strain, and it can be used as sensor actuator. So sensor actuator for the whether hydraulic or pneumatic or electrical or magnetic components, and these are applied. Smart materials simulation like thermo-responsive materials. Thermo-responsive is the ability of material to change properties in response to changes in temperature. They are useful in thermostat and in parts of automated and air vehicles. See, you can see this tumbler when temperature coffee are poured, the image will change in outside shape. Similar way, electrochromic material is the ability of material to change its optical properties when voltage is applied. When the supply, it will the LCD. They are using LCD and cathode lithium. When power is there, there is some color impinging. Otherwise, it will be normal. So these are the also one of the smart material, the Kingfisher Japanese bullet, the air fluid dynamics concept was found comparing the that is called biomimetic materials, biomimetic materials. And these are some how the Volgro was concept from the Burr, natural to artificial comparative. Smart material, natural smart material is compared with the artificial smart materials. And fluorines, these are spherically gauged molecules with carbon atoms at the corner of the polyhedral structure consisting of pentagon, hexagon. These are usually used in polymetric use of smart systems. They are used in electronics and microelectronic device, superconductor like this, electronics like a nano tubes like that. The shape is seems to be like that. The biomimetic materials we have seen now. Same another example is shown. And then these are the fluorines. Fluorines also one of the a lot of videos are there, but video sound we will see last. Suppose sound is coming, and then smart. This one smart gels, tablets. These are the gels that can shrink or swell by several order of magnitude. Some of these can also be programmed to absorb or release fluids, respond to a chemical, physical. These gels are used in such as food, drug delivery, organ replace, chemical processing like this. These are shape memory alloys. We already studied in the basics only how it was. This basic 1932 onwards like this growth. Titanium, nickel, titanium growth. Video you will see last if voice is coming, and then application aircraft, and then dental robotics, reducing vibration, helicopter. These are the applications. Merits and demerits: biocompatibility, simplicity, compactness, safety. These are merits. Demerits: more expensive, low energy efficiency, complex, limited bandwidth. And these are the application real life. Nanomaterial, real life stimuli triggering. What will the nanotechnology is a rapidly developing field entering the world of smart material and taking them to the next level. They may incorporate nano sensor, nano computer, nano machine into their structure, which may enable them to respond directly to their environment. These are the materials. These are the simulation which both will add when the simulation will go this, then it will act as a smart material. That is called a nano smart material because it is simulated by nano materials. And this one stuff getting smarter. How the smart materials, what do all these things have in common? That is, we might not realize, but smart materials are starting make real impact. That is kettles that change color when they boil. This is the kettle. When the boiling, the color is changing, and the garments that plug into the MP3 player. So now the garments is added with the MP3 player, the coat, raincoat, or things. Batteries that report their condition. So batteries report their condition. So yeah, what is the level of battery? How much percentage of charge it will show? That is the smart material. These are the examples of application of exhibiting smart behavior. And let us see this. You can get special material that can change different condition. That is, smart material react their environment. Smart material change their properties, heat, light, and they often change back to the original when heat. You have seen in the video when the smart material is that is when subject to heat, then it will go to original shape. Again, when you take it out, you can. Then polymer is useful for molding plastics. This example, completing complex shapes, everything's jewelries, and these are the examples. Thermomaterial, the viscoelastic polymer examples, viscoelastics, and this one thermochromic materials. Pigments change back to their original color when they cool.
Sorry for the disturbance. Next guest is waiting.
Then they can be used in paints to create images that change when the thermochromic inks can be printed onto the range of materials such as plastic and paper. Thermochromic films are sheets that have been printed with the thermochromic ink. So there is a ink is also acting as a smart material when over the thermochromic films. Display changes. Then photochromic pigments change color in response of light. By applying light, the colors change in the photochromic. They are explaining this. Photochromic inks can be used to print T-shirts. T-shirts you are seeing with the designs that only show they can put into spectacle lenses to make glasses also. There is a color change. The sunglasses when it's sunny and because of the temperature. And see this photochromic material. Lenses become darker when increased ultraviolet light. But glass changes from transparent to opaque as level of light increase. See, in the building also they have kept a smart material glass. When the sunlight comes, there is a transparency, and during night there is no transparency. Similarly, the mini rainbow paint option give the rainbow effect in bright sunlight. The car bonnet will seems to be rainbow effect, but during there is no sunlight, the color will change. The color changing is band, wristband indicate when sun cream needs to be reapplied. When it's time to move the shade, the sun is over, like that t-shirt, because of light. And fluorescent pigments, fluorescent lights we have seen. Fluorescent pigments store light and slowly release flow and growth. The fluorescent, you can see these safety guards for traffic person or firing person hearing the code.
Good morning, sir.
Different, sir.
Madam, ஏதாவது ஒரு காம்படிஷன் போட்டு உடனே அப்ளை பண்ணிட்டு மேடம் முடியல மேடம்.
And these are nanotechnology. Finally, this one, you will see this.
இப்போ நீங்க ஐடிசி வந்து
We are concluding.
மேடம் ஃபார்மலிஸ்ட் அமைச்சிருக்கேன் பாருங்க.
The audio is there or no?
ரெஜிஸ்டர் பண்ண வைக்கணுமா? இது நான் கொடுத்த ஐடியா தான் இது. அவங்க வந்து என்ன சொல்றாங்கன்னா சிஓ சார் 4 மணிக்கு லிஸ்ட் கேக்குறாரு.
Sir, audio is coming. Start video. Cut ஆகுது.
சார் வாய்ஸ் வந்து கேட்கல சார். ஹலோ,
வீடியோ மட்டும் கேட்கல. அது
வீடியோ மட்டும் ப்ளே ஆயிட்டு இருக்கு, ஆடியோ வந்து கேட்கல சார்.
வரல.
ஓகே ஓகே ஓகே, வீடியோ வீடியோலயும் அந்த ஆடியோ வாய்ஸ் சார், அதுக்கு தான். தேங்க்யூ.
அது திங்க் பண்ணிட்டேன். ரெஃபரன்சஸ் வில் see வீடியோ 2-3 வீடியோ இருக்கு, என்ன பார்க்கலாம். அது வாய்ஸ் வருதான்னு தெரியல. சேம் So, if you want, we'll conclude our this video. Already same concept this only. Already we have seen. Carry on. Okay, sir. Complete.
Sir, okay. Thank you, Dandapani sir.
Sir. Okay, sir.
Sir, thank you, sir. Another guest is waiting. That is a problem. Dr. VIJAYA RAMNATH is
Anything is there? Any?
Yeah, I request participant if you are having a specific queries or questions, kindly interact with our guest.
Okay, sir.
Yeah, okay. Thank you, Dandapani sir. I will share your contact to all the participants. If they are having any specific questions, they will contact you in the future, sir. Thank you very much, sir. Thank you, sir. Thank you.
Okay, sir. Thank you, sir. Thank you for
Yeah, thank you for your presence here. Thank you very much, sir.
Thank you, sir. Thank you.
Thank you, sir. Prabhudas sir, are you ready? Prabhudas sir?
Yes, sir. We'll start next session.
Yeah.
Okay,
Dr. VIJAYA RAMNATH sir. Good morning, sir. Dr. VIJAYA RAMNATh sir. Good morning, sir. Kindly check பண்ணிக்கிறேன் ஒரு நிமிஷம் Prabhudas. Yeah, Dr. VIJAYA RAMNATh sir, are you ready?
Good morning, sir. Ready, sir.
Yeah, good morning. Sorry for the delay, sir. Sorry for the delay.
No issues, sir.
Okay. Thank you, sir. Prabhudas, carry on.
Okay, sir. So thank you, Dandapani sir, for
Sir,
being.
Dandapani sir, kindly stop your screen sharing. Dandapani sir. Dandapani sir. 1 minute, please. Punshanmugam sir, PSK.
Hi,
Yeah,
sir.
thank you, sir.
Okay, sir. Thank you, sir.
Thank you, sir.
Okay.
Prabhudas sir, you carry on.
Okay, sir. So we'll move on to the final session of this STTP program. So hearty welcome to our beloved professor and head of the department, Sairam Engineering College, Dr. B. VIJAYA RAMNATH sir. So on behalf of Sairam Institute of Technology, Mechanical Engineering Department, we welcome you, sir. And let me brief the profile of the speaker of this session. Dr. B. VIJAYA RAMNATH sir, professor and head of the department, Mechanical Engineering, Sri Sairam Engineering College. So has completed his Bachelor's Engineering from Madras University, Masters of Engineering from Madurai Kamaraj University, and doctoral program from Anna University. He has a vast teaching experience of more than 20 years, research experience too, and he has attended a number of
ஒரு 1 hour code நான் ஒரு mail ID அனுப்புறேன்.
Give me in WhatsApp.
I'm sending it.
First.
He has undertaken, sorry for the disturbances. He has attended a number of workshops, conferences, and FDPs. His publications are around 148 and 192, both in national as well as international conferences. Sir has published 2 patents and has guided 6 PhD scholars so far, and 12 more are doing PhD under his esteemed guidance. His achievements includes, so he has received a Best Teacher Award from Sairam Engineering College and also from Lions Club, and he has acted as session chair for various international conferences and has received Best Paper Award for his research work from a reputed journal, and he has received Dr. Radhakrishnan Gold Medal Award given by Global Economic Progress and Research Association, Tiruvannamalai. He has received Chhatra Vishwakarma Award for his project entitled Hands-Free Vehicle for Disabled. So from AICTE ECI Chhatra Vishwakarma Awards in the year 2017. He has been a resource person for various workshops, international conferences, and FDPs, and he is advisory committee member for international conferences in India as well as abroad. And he is the editor in international and national journals, to name a few. So International Journal of Engineering Research and Innovation, California State University, USA, Editor-in-Chief of International Journal of Mechanical and Manufacturing Technology since 2013, and many more international journals. He is the research supervisor, recognized research supervisor of Anna University, Wales, AMIT, Sri Chandrasekhara Saraswati Vishwa Mahavidyalaya University, St. Peter's University. So his accomplishments are more enough to brief here. So we are privileged to have you, sir. So kindly take over the session, sir, please.
Okay, thank you, Rolas. Is it audible?
Yes, sir, audible, sir.
Yeah, yes, sir. Audible, sir. Audible.
First, I thank the organizer of the program.
கொஞ்சம் விட்டு கேக்குது சார். கொஞ்சம் வாய்ஸ் மட்டும் பிரேக் ஆகிற மாதிரி தெரியுது. ஹாட்ஸ்பாட் போட்டு கொஞ்சம் பிரேக் ஆகிற மாதிரி தெரியுது சார். பிரபுதாஸ் இஸ் இட் கிளியர் ஃபார் யூ? சார் ஓகே சார், கண்டினியூ சார்.
ஓகே சார், இஸ் இட் கிளியர் நவ?
இல்ல கொஞ்சம் பிரேக் ஆகுது விக்ரம் சார். ஸ்லோவா பேசுங்க, பொறுமையா பேசுங்க. ஓகே சார், ஓகே சார், வி கேரி ஆன் சார். ஓகே சார். Sorry sir, voice is not clear sir. Sorry sir. Hello.
I will cut my video so that the content will be much better. Sir, இப்போ clear இருக்கா சார்? சார் இப்போ clear இருக்கா? ஹலோ சார், இப்போ clear இருக்கா? சார் சண்முகா சார்?
Yes sir, yes sir. இப்போ ஓகே சார், பேசுங்க.
இப்போ clear இருக்கா?
ஓகே சார், now it's okay. Okay, thank you.
வீடியோ கட் பண்ணேன். வீடியோ கட் பண்ணிடுங்க
சார்.
வீடியோ கட் பண்ணிட்டேன்.
Yeah.
Okay.
Carry on sir. Okay, thank you.
Okay, good morning, present here. First of all, I thank the organizer of the program, Sri Sairam Institute of Technology, Principal Panikumar sir, Coordinator Dr. Sandhu sir, and faculty members of Sairam Institute of Technology Mechanical Engineering Department, and who introduced me, my beloved student Prabhudas. One and all, thank you for having given this opportunity to have this session in the field of nano composite materials. At the outset, I thank the AICTE for having given a chance to be a resource person for this program. So first, I want to. Is it audible now?
Yeah, okay sir. Okay. கொஞ்சம் பிரேக் ஆவறமே கொஞ்சம் ஃபீல் ஆகுது. ஹெட்போன் இருக்கா சார் உங்கள்ட்ட? ஹெட்போன் வச்சிருக்கீங்களா?
இல்ல, ஹெட்போன் வீடியோ கட் பண்ணிட்டேன்.
வீடியோ கட் பண்ணிட்டீங்க. கொஞ்சம் டிஸ்டர்பன்ஸ் இருக்கு. பரவாயில்லை, you can carry on sir. No issue sir.
Okay sir.
Can carry on. Okay. Participant kindly put mute to mode. Sir, Vijayana sir, voice கேட்கல. Unmute பண்ணிக்கீங்க sir.
இல்ல சார் இப்ப ஷேர் பண்ணிட்டு இருக்கேன். ஷேர் பண்றேன்.
ஓகே ஓகே ஓகே. தேங்க்யூ சார், தேங்க்யூ சார்.
சார் ஷேர் ஆயிடுச்சா சார் இப்போ ஸ்கிரீனு?
ஸ்கிரீன் ஷேர் ஆகல சார். உங்களோட
அனுஷ்மா சார்
காமிக்குது. இல்ல அந்த ஸ்கிரீன் ஷேர் ஆகல சார். நோ.
ஷேர் பண்ணிரலாம்.
டாக்டர் விஜயராமன் அந்த இதுதான் காமிக்குது.
இப்போ வந்துருச்சா?
ஏன் வரல சார்? உங்க நேம் அந்த
கொஞ்சம் ஸ்லோவா காட்டாது சார்.
ஓகே. யா எஸ் ஸ்டார்டிங் சார்.
இப்போ காமிக்குதா?
காமிக்குது சார். காம்போசிட்ஸ்னு போட்டிருக்கீங்க. காம்போசிட்ஸ்.
சார்
ஓகே 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 ஓகே.
ஓகே. So sorry for the disturbances and delay in connectivity. So I thank the organizers of the program. So I think more than for last 5 days you people having the very good and having the lot of information about the smart materials. So as I requested with the organizer coordinator Sanmu Sundar sir, I already want to have the session on this nano composite materials and how its roles in the field of smart materials. So first of all, let me take what you mean by composite materials. I think everybody aware of what is composite materials. The composites are the classes of materials where two or more materials with the resistance and combined together to give you a single structure with an interface. If frankly speaking, composite is nothing but a material which contains two or more materials. I used to give an example for the composite material is a mixture. For example, a mixer contains more than 4 or 5 ingredients. For example, it contains a karabundi இருக்கும், அப்புறம் வந்து ஓமப்பொடி இருக்கும், வேர்க்கடலை இருக்கும், அப்புறம் வந்து பொட்டுக்கடலை இருக்கும். ஓகே, everything available in are all available in the mixer. So if you individually taste the groundnut or karabundi or omapudi, it gives its own taste. But when you going to combine all 4 or 5 put together and if you're going to taste it in the form of a mixer, it taste is entirely different. That mixer is a composite material. So is it audible?
Yeah, yes sir, audible sir, audible sir.
That the mixer is normally known as the composite material. So it will going to give the property of the materials which will going to form the complete composite materials. In composite, if you see, there are two main factors or the interfaces. First one is the matrix material, another one is the reinforced material. So for example, this I want to give one more example, preparation of laddu. Everybody aware of laddu, Tirupati laddu or whatever, Modi laddu, whatever may be. Laddu pathina, there are two components. One vandu and the bundi irukum, innonu vandu sakara pagu irukum. That is the sugar slurry as well as the bundi. So that sugar slurry is known as the matrix material and the bundi is known as the reinforcement material. By preparing the laddu, we are going to make a composite. So laddu is nothing but a composite material which contains both bundi and sugar slurry. So these two are the example for the composite material. I think everybody basically aware now understand what you mean by composite materials. Mixer which contains the various ingredients in order to give the different taste. Which it will going to give the taste of all the ingredients like kara bundi, omapodi or groundnut or whatever maybe. Similarly, the laddu is going to give the taste of both bundi as well as the sugar slurry. So with this brief introduction, I want to step into this is the research done by my research scholar in the field of nano composite materials, metal matrix composite materials with nano. That is the CNT powder. So before starting, I want to give one more clarification for the audience. What is metal matrix composite materials? In composite materials, we are having the different or minimum 4 or 5 categories of composite materials. First one is the fiber composite materials. Either it may be the natural fiber or artificial fiber. Second one is the metal matrix composite material. Third one is the polymer matrix composite material. Fourth one is the ceramic matrix composite materials. Here the matrix stands at the interface which will going to form the material. As I told that the sugar slurry is the matrix material. If I going to use metal as ingredients, then it is known as a metal matrix. If I going to use the fiber as a reinforcement, then it is known as a fiber matrix. If I going to use the polymer as a reinforcement, then it is known as the polymer matrix composite materials. So why normally we are going for the composite materials is important point of discussion now. So the composite material will give high strength, high stiffness, toughness, very good density, good wear resistance, and damping capacity. So nowadays all the automotive manufacturers are replacing the conventional material by using the composite materials in order to have the very good damping capacity as well as the specific models. So since I want to discuss about because the time is running, since I want to cover the research part of this my presentation, I want to give the overall view of this research content. So in this presentation, I am going to give the aluminum metal matrix nano composite. Aluminum metal matrix nano composite. Here, in aluminum metal matrix composite are normally classified into particle reinforced, viscose or short fiber reinforced composite, continuous fiber. So, performing or fabrication this continuous fiber reinforced aluminum metal matrix composite is somewhat difficult as compared to the other type. And the last one is the hybrid aluminum metal matrix composite. This hybrid metal matrix aluminum metal matrix composite is nothing but the composite materials which contains more than 2 reinforcement. In this work, we used LM25 aluminum alloy, which will going to act as the matrix material. And we used 2 reinforcement, namely silicon carbide. I think everybody aware of the silicon carbide. Silicon carbide is a compound of silicon and carbon. It is the most commonly used abrasive material and is the hardest material commercially named as a carbon. So what are all the advantages of using silicon carbide? So you have a very high strength, low density, high elastic modulus, and high thermal conductivity with the low thermal expansion. So these are some of the property and colors and kind of the salient features of the silicon carbide. And then we use carbon nanotubes. So since you use carbon nanotubes, this work normally termed as the nano composite material. I think everybody aware of the CNT. CNT describes a family of nanomaterial made up of carbon. The CNT are generally arrangement of carbon in tube structure, which is in a nanoscale method. So CNT is 10,000 times thinner than our human hair. So our human hair size is in terms of microns. It is 10,000 times thinner than our human hair. There are various types of CNT material: single wall, double wall, and multi-wall carbon nanotubes. So these are some of the introduction about the carbon nanotubes and multi-wall carbon nanotubes. So these are the properties of carbon nanotubes. The purpose for which we are using the nanotubes, that is the CNT in this research work, in order to have the very good and very high tensile strength. So there are various process of manufacturing this metal matrix composite, nano composite. This is what I say, that is still casting process. There next one is the liquid state, next one is the solid state.
விஜயராமன் சார் உங்க வாய்ஸ் ரொம்ப கம்மியா இருக்கு. விஜயராமன் சார்
இல்ல சார், சைடு சவுண்ட் வருது சார்.
சவுண்ட் வருது
சார். பார்ட்டிசிபென்ட் கொஞ்சம் மியூட்.
Yeah, participant only, kindly mute all. Okay sir, thank you sir.
In fabrication of composite, there are 2 main methods: liquid state and the solid state. So solid state, we are having the powder metallurgy process, ball milling process, and friction stir processing process. And in liquid state, we are having the stir casting, skew casting, and the spray casting process. Generally used, that is the liquid state is the stir casting process because it is easily available and it can be easily controllable. In case of solid state, we are having the ball milling and friction stir processing. Among that, the best one and the easy one is the powder metallurgy process, because we can easily get the sample from the powder metallurgy process. But the one of the major drawback in the system is the cost of the processing, because before you go into fabricate the sample, we have to design the die. It is a completely the die. You have to design the die and you have to fabricate the die by using the wire cut process. And the die cost itself comes around 75 to 80,000 for making a sample. Then we have to prepare by combine that is mix the powder with the CNT or whatever may be the nano content in the ball milling process. Then from the ball milling we are going to provide the powder metallurgy based composite samples. Then you have to perform the sintering process. Then you have to test for the its mechanical properties. It is an entirely different sequence. But in case of stir casting process, directly we can melt the aluminum. We can add the reinforcement like silicon carbide or boron carbide or aluminum oxide, whatever we want to manufacture based on our required properties, and we can add the CNT also. So in this research work, my scholars use stir casting process. Stir casting, it is a various among various manufacturing method. It is a simple and cheap and easy fabrication method. So because in stir casting setup, if you see in the market, it's available from 8 lakhs to 12 lakhs cost. But if you use, you can easily convert a vertical milling machine into a stir casting process by providing a stepper motor. So it is a easy method. So that's only I am coming to say that it is a very easy and cheap method. If you are not having any contact or the slot for manufacturing the aluminum metal metals composite by using the stir casting actual setup, you can convert your drilling machine or your vertical milling machine into a stir casting setup just by modifying the motor speed and some timers. You can easily fabricate your stir casting setup. Next one is these are all the various stir casting advantages, the purpose, and the stir casting. The particle often tend to form among it. This is very, very important. So the particle will accumulate themselves. In order to avoid that accumulation, normally we are going to perform the stirring process. So the stirring process also we can normally they are using the only 2 blade. This work my scholar used 3 blade with 60-degree angle of inclination. So in conventionally speaking, I think everybody aware of the Tamil. I know everybody aware Tamil. Okay, இந்த நம்ம இது பண்ணுவாங்க வீட்ல வந்து தயிர் கடையிறதுக்கு மத்து வச்சிருப்பாங்க. I think it is nothing but the making or preparing the lassi in our juice stall. Preparing the lassi is nothing but the stir casting process. So we are having that mattu stir, and we are going to have the sugar, ice, curd along with some water in a jug. Then we are going to place that jug under the stir. We are going to switch on the motor. That stir will completely mix the curd, sugar, and some of the ingredients, whatever you want to add along with your lassi, it will get mixed. So that preparing that is lassi is a basic example for the stir casting process. But lassi is very, very cool. But here we are going to maintain the temperature of 730 to 850 degrees Celsius with the speed of 500 rpm. So this is the basic experimental setup of the stir casting process. Here we are having the transformer and the dimmer for regulating the speed. And here he used a 4-blade stapler with some angle of inclination. So he carried out the 3 types of research component: 2-blade, 3-blade, and 4-blade with various inclination. And this is a furnace door. Is used to loading and unloading the crucible for the stirring process. And in the bottom we are going to have the molten aluminum along with the ingredients. So this is the furnace of stir casting setup available in MIT. These are the various stages of preparing metal matrix composite. First one is the melting of matrix. So this melting of matrix is performed in a stir casting setup. Then feeding of the reinforcement. So we have to add the reinforcement at the exact time. So if you not properly maintain the time, what will going to happen? Sometimes the reinforcement will vanishing, or sometimes it not be properly mixing with the molten aluminum. So which in whenever you are going to take the SEM or you perform the XRD, you can't get the very clear images. And the stirring of the composite, and the pouring of the composite in a die. So you have to prepare the metal die either by manual machine cutting or by using the CNC. You have to prepare the die, and you have to allow it for solidification. Minimum 14 to 18 hours you should allow it for solidification. Later you can take the composite sample and you have to machine. So in this, what are various samples manufactured? So we maintain it as a category 1, 2, 3. Each category we have the sample 1 and 2, 3, sample 1 to 3, and sample 1 to 3. And these are the various percentage of multi-wall carbon nanotubes and silicon carbide reinforcement. So he maintained in the C1 only we used CNT with 0% of silicon carbide. In C2 we used 0% of CNT and 246% of the silicon carbide. In C3 we used both 0.25, 0.5, 0.75% of the multi-wall CNT and 246% of the silicon carbide. So you can do lot of combination. So it depends on the cost involved as well as the time of fabrication. So these are the various samples manufactured for the above said samples: C1S1, C2S2, and C3S3 with pure CNT with the pure silicon carbide with the silicon carbide and the CNT combination. So after fabricating this composite sample, we have to machine it for the further processing. Here, the ultimate aim is to perform the various, to evaluate the various mechanical characteristics of the material. So we perform 4 mechanical tests. First, you have to find the density test. So how best the composite sample is manufactured. Second, we perform the tensile test. So everything I think as per ASTM norms, you can perform the samples. So now whenever I having this presentation, normally people ask that how we are going to fabricate the sample. So a lot of manufacturing setups are available. So by using the abrasive jet machining, we can easily cut this sample as per AICTE norms, because abrasive jet machining and abrasive water jet machining are the scene based. Once you give the that diagram in form of AutoCAD file, then it will automatically convert into the machining part and it will going to cut. Otherwise, you can perform it by using a manual cutting also. So the maintaining the ASTM standard and dimension, the exact properties are samples. So this is the tensile sample of C1 and the sample of C1, C2, and the C1, C2, C3. So I already told that what you mean by C1, what is CNT, C2 pure silicon carbide, C3 combination of CNT and the silicon carbide. We have to perform the compression test by using the ASTM standard of E909 standard. And so the tested specimen samples are shown here. So C1, C2, and
Participant 131, kindly mute yourself, please. Thank you.
so these are the compression. I think I handled tension test, compression. Then we performed the impact test as per ASTM D256. So these are the various samples of the impact test: C1, C2, and C1, and we performed the hardness test by using the so the hardness we can have only a small indentation. So hardness is nothing but the resistance to indentation is known as the hardness. So by performing hardness test, we get the hardness of the material. There are 3 samples. And last we performed the wear test. So what are the wear characteristics of the material, fabricated composite material? So we used the pin on disc apparatus available in the Kanji Sankara University. So this is the wear testing of composite for the pin on disc apparatus. So the disc material made up of steel. But now I want to discuss about the result. The result is a very important part, because since this presentation is mainly based on the research part of a scholar, so I want to give the output. So as I told earlier, so there are 3 categories of composites were fabricated: C1, C2, and C3. C1 contains aluminum with multi-wall CNT alone. C2 contains aluminum with silicon carbide. C3 contains both aluminum, that is reinforcement like silicon carbide, and multi-wall CNT. So density test, you will see the density of the C2 is higher than C1 and C3. So it is the category of sample. The theoretical density increases with the percentage of silicon carbide. since the C2 contains the pure silicon carbide alone along with the aluminum, so the density of the silicon carbide composite is higher than other two. And result of density test. So normally, if you see the hybrid composite, normally giving the very high tensile or some of the mechanical properties, because it's normally having the that is a combined properties of the both reinforcement. In this case, it is a combined, it having the property of silicon carbide as well as the multi-wall carbon nanotubes, which is available in the C3. So out of this, if you see the C3S2, that is the category 3, which contains aluminum and aluminum along with the silicon carbide and multi-wall CNT, having the very high tensile strength of 186 megapascal with the yield strength of 120 megapascal. This is only due to the presence of the multi-wall CNT along with the silicon carbide. So this graph shows the comparison of the three types of samples. That's only for tensile strength, category 1, category 2, and category 3. As I told earlier, this category C3 gives the very good performance. And the next one is a compression test. So result of compression test shows that again the C3S2 having the very good, having the very high compressive strength with the that is taking a compressive load of 97 kilonewton. So this is also mainly due to the presence of multi-wall CNT. If you see that C2 and C3 performance are very closer, because this compression property mainly, improved compression property mainly depends on the presence of multi-wall CNT. So since C2, that is a C1 and C2 contains the pure CNT alone as well as the silicon carbide alone, this C3 having gives the combined effect of both materials. That's only normally the research is mainly focusing on performing the hybrid composite materials. So the above first two are mono composite materials. The third one is a hybrid composite materials. You can add one more reference one also. For example, I want to prepare a fabricate a brake pad or some of the wear property or some of the materials which are used for the corrosion resistance application. I can introduce the aluminum oxide also. So it will become the three reinforcement: aluminum oxide, silicon carbide, along with the multi-wall CNC. Then the property may be complete. There is a drastic change in the property of the materials. So my humble advice here is that not information here is. So first you have to decide the purpose for which we are going to fabricate the composite. It's very, very important. So you have to fix your application and then you have to work. So normally nowadays, a lot of people what they are doing is they are doing fabricating composite. They are getting some values. Based on them, they are proposing the application. It is not, sometimes it is not suitable for their publication. So first you have to fix your application, and based on your application, you try to prepare the composite material as per the again the table column is shown in the form of the comparison of the composition that I already told, and this is the impact test value. So there is if you see there is no much difference between the impact test value, because it is the impact is nothing but the energy absorbed by a material in terms of joule. So C2 and C3 having the same material because both contains the silicon carbide. But C3S3 having a very good hardness as compared to other 8 samples manufactured. That is 3 in C1 and 3 in C2 and 3 in C3. So if you see out of that 4 tests, whatever we performed earlier, that C3 gives a very good performance. So again I come to say that the hybrid composite having its own impact on the better giving the better mechanical property and behavior of the materials. Sanmu Sundar sir.
Yes sir. Yes sir. Solluங்க sir.
Yes. Next part is completely wear analysis. Shall I have 10 minutes more? Or yeah, shall I wind up?
12:30. 12:30. No, 10 minutes. Another 10 minutes.
12:30. Okay, sir.
Okay. Thank you. Thank you very much.
Okay. So in order to analyze the wear of the material, so the wear of the we are performed by using the so the above four examples, so we started the material with very good mechanical property. So that the mechanical property mainly was set for performing the VR analysis. So we performed L27. L27 nothing but the orthogonal 27, L27 experiments were conducted by the variation of the load, sliding velocity, and sliding distance. These three are input. If you see this table, I think it is visible. So this load, sliding velocity, and the sliding distance are the input parameters. These are three levels. So we got around 27 experiments. We calculated the specific VR as well as the coefficient of friction. So that ANOVA calculation. So ANOVA calculation also shows the percentage of contribution. So out of the when we see the above table, what are all the VR parameters? What are the coefficient of friction? That which plays a vital role is the load. The load which is going to apply on the material having its own effect because the percentage contribution of load is 62%. Then the sum of the sliding speed has 6% and the sliding distance has the 4% of the contribution. Now this is the SN ratio. That is a signal to noise graph. So which shows the effect. So if we see this diagram, so based on this, we are going to have this plot SN plot. So this SN plot and ANOVA table will be plot for the all for the first one for the specific area, second for the coefficient of friction, third for the so we can have the so we calculate only two specific rate and the coefficient of friction. Hence it is calculated for the ANOVA was performed for the two things. If you are going to have two more property, if you are going to evaluate two more property by the existing this is this table. So then the three are input: the load, sliding distance, sliding speed. The output are only the coefficient of friction as well as the specific variate. Further, the ANOVA has been performed and this was compared and we calculated the percentage contribution of the each factor. So here the role of CNT in reduction of wear behavior in aluminum silicon composite. This is the final essence of the research. The weak bonding between the CNT metal lead to the easy slide or roll between the contact surface. So why this aluminum CNT silicon carbide composite having a CNT combination will give the very less wear rate is. This point is very important. The weak bonding between the CNT metal leads to easy slide or roll between the contact surfaces and minimize the direct contact between the surface, thus results in the decrease in friction coefficient of the composite materials, which in the specific. So these are some of the that is I think my previous speaker, Dr. DHANDAPANI, gave the very clear picture about the scanning electron microscope, its performance and its working. So here I want to give some of the salient features of the purpose for performing the SEM analysis. It is not SEM analysis, it is a morphological analysis by using the SEM, scanning electron microscope. So here if you see some blowholes are identified in composite and some voids are available. This is similar to the casting defects. Some of the casting defects which are being encountered in the conventional casting process. And some of the fracture also identified in the casting and the brittle fracture. So due to the improper cooling, the voids are the accumulation. Sometimes if you see the accumulation of reinforcement may be observed, it is due to the improper stirring of the material and the crack propagation, again voids and cracked surface. So what are all the drawbacks of having this type of failure or some of the surface property? It will going to reduce the mechanical property or the behavior of the material. So what are the steps we have to take that? So whenever perform this, there is a shell casting process, we have to predefine some of the things. So the proper temperature must be maintained, proper stirring speed must be maintained, the proper power supply should be there. For example, whenever, for example, I'm going to add the reinforcement, at the time there is any power fluctuation, the stirring speed will be reduced. I want to maintain the 800 RPM, but it may be reduced to 650 RPM. What will going to happen? The complete stirring cannot be obtained, which will going to have the accumulation. That is, it will going to accumulate the reinforcement here and there, which will be clearly shows in the XRD as well as in the SEM analysis. So these are the scanning analysis. XRD also performed. That is a index also performed to know the content of the each and every reinforcement and their sources. Okay. Some of the that is a very load condition, 5 Newton load, 10 Newton load for the rear surface. So we have on surface we are going to perform the EDAX, and the EDAX images are clearly shown. I think so. Since I am using the tab, you can see here the silicon carbide. Presence of silicon carbide is identified. So whether it is a silicon carbide composite, we can easily identify the. So due to some network compute, I think you people are not properly using my side. I think now it is okay. That's all. Sir,
yeah, thank you, sir. In my area also the same issue, so that's why I'm off my video. That is the problem.
Yes, sir.
Yeah.
Okay, sir. Sir,
thank you.
I'm finishing. Thank you, sir. Thank you.
Yeah, thank you very much, sir. Thank you, Dr. VIJAYA RAMNATH, sir. Came over here and present your work on composite research using a design of experiment and Nano methods and SEM analysis of composite material. Thank you very much, sir. Thank you very much. And request participants, if you are having any queries, kindly interact with our HOD professor, mechanical department, which is Sairam Engineering College, Dr. VIJAYA RAMNATH, sir. If you are having any specific questions about composite material processing and development, and he has vast experience in composite materials, kindly interact with our guests if you are having any specific queries.
Hello, sir. Good morning.
Yeah, good morning. Yeah, tell me.
I am
hello.
The phone number, sir. If any having doubt, you can contact
me.
Yeah, one participant is asking questions, sir. 1 minute, sir, please.
Now you ask your doubt, I will clarify. Now you ask.
Yes, speak, sir. Please speak, sir.
Now you ask. No problem.
Thank you, sir. Thank you, sir. Thank you, sir. This is Muthukumar only.
Okay. Thank you, Muthukumar, sir. Thank you, sir.
Good morning, Professor. Good morning, sir. Thank you, Professor. Very nice presentation, sir.
Thank you, sir.
Okay. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir.
Thank you, sir.
Yeah, dear participants, I now I can post the feedback link for the second section. Kindly fill the feedback link for the second section. And one more important announcement. This is our final day of AICTE-STTP program. I thank all the participants and also our guests for came over here and graced this AICTE-STTP program 6 days. I request all the participants who are yearly registered for this program and attended the past 5 or 4 day section, whatever it may be. But the final assessment exam is very, very important. Kindly join us at 3 o'clock. 3 to 4 is only a test hour. And that is purely only a test and feedback section. And kindly give some valuable feedback to the organizers of our STTP program. And if you are having any doubts and queries, please contact me. And the test section is very important. Kindly attend the test before leaving this section. That is the third section. And we will meet you 3 o'clock sharp. 3 o'clock, the test questions will be posted in the chat box. And you are not closing your, that is log out. You are not log out, you are log out from the section. You just on your section, the Zoom itself, then only the attendance will be calculated. You just on the Zoom ID and you will take the test. If you are willing to on your video,